Everybody for joining here. Sorry, it's been a few weeks since I've been in town. I've been out traveling around the, not, I will say world, but sort of the East Coast from Labrador to Virginia, doing a lot of research or radar work, the super darn and things like that. But
Labrador, that's a
yeah, that's a fun
serious
one.
trip. Yeah.
Yeah, we have a radar site in Labrador, so. Yeah, it's a not very big place and not a lot of reason to go there otherwise, but.
How long were you there?
We were there for about a week.
Oh, that's cool.
Yeah, we saw the first snow, I think, for Labrador. This was
Oh, wow.
2 weeks ago, so.
Cool.
Yeah, winter is out there. It's starting to get cooler here, I guess, eventually, but
Yeah, it's coming.
yeah. But for today, we have Davis Earley, who's gonna show us some things on some more atmospheric sciences.
Yeah, so thanks again, everybody, for giving me the chance to be here. Like he said, my name is Davis Earley. Third year PhD student under Elena Lind, and I'm really excited to be able to show everybody here some of the research I've been working on to progress towards my dissertation. So like he was mentioned just a second ago, my research is less focused on upper atmospheric or even really space-based measurements. It looks instead to interactions within some of the lowest atmospheric layers, more specifically with the interaction of trace gases in the troposphere. Now, trace gases are ultimately just molecules that make up a small contribution to the overall air composition. However, even with these small contributions, they can have some pretty serious impacts on both our health and the health of the environment, with them being some of the largest causes of air pollution and responsible for multiple different respiratory illnesses such as allergy sensitivities, asthma, and even being some of the leading causes of lung cancers. Typically, these trace gases are emitted from various artificial sources like industry or vehicular emissions, with even some very large quantities of these trace gases being able to travel over fairly long distances into areas that otherwise would not be close by to these sources, therefore interacting with areas that aren't necessarily particularly of major interest. And so in order to fully understand how these trace gases are interacting both with the atmosphere and ourselves, it becomes very important to be able to measure just how much of these trace gases are in any particular location at any time. And so one popular method of these types of measurements is known as differential optical absorption spectroscopy, or the DOAS technique. Now, the basic operating principle of DOAS is to not necessarily directly measure these trace gases themselves, but to measure the absorption of light as this light passes from its source to a detector and determines how much of that light has been absorbed as it's passed through along this specific path. This interaction is characterized by the Beer-Lambert law, which can be seen in this equation to the right, and demonstrates that simply by measuring how much light exists at a detector and a proper estimation of how much light is existing at its source, you can determine wavelength by wavelength how much of that light has been absorbed as it's traveled along this path, ultimately representing a concentration, kind of an average aggregate concentration that exists along this path. Ultimately, the final data product of this DOAS method is a vertical column density, which represents an averaged path integrated concentration that stretches from the bottom of the surface to the top of the troposphere.
I apologize. Can you go back?
Sure thing.
Last time you showed me this, I told you I was going to come back and make a comment, and I forgot to do it. But in that equation there, the Beer-Lambert law, the x cubed plus x squared plus x, that's the cross section.
No, so the cross section would be your sigma j, but this ultimately is kind of a modified Beer-Lambert law equation that separates like the wideband spectral effects, like atmospheric scattering and some of the larger structures within these trace gas cross sections with the smaller band.
So what's x?
So that's the like a polynomial fit that is estimating these wideband.
Right, so there should be some constant, ax cubed plus bx squared plus cx and plus d would usually be there, something like that. Do you know what I'm saying? It can't be just x cubed plus x squared plus x.
Right, I think this was just kind of a general equation without really looking in too much specifics, just to kind of illustrate and kind of in broad terms how the actual fitting process occurs.
Okay. maybe to make me happy, we at least put an F in front of it.
Sure,
F
I
of
can-
X cubed. And remind me again, what is X? Not
So-
wavelength?
No. X is just so these are like just a polynomial fit of the wideband absorption and scattering effects that aren't necessarily are fairly over sufficiently small wavelengths will not necessarily be showing up.
Yeah, I'm just, what's the independent variable in that fitting?
So yeah, it would be wavelengths. It's just
So is it X wavelength?
no, it's X is a function of wavelength.
Let's just put an F there, if
Yeah.
that's okay. And
Yeah, well-
really, if X is a function of wavelengths, I would just make that F of wavelength.
Sure thing. Yeah, that's easy enough. So then ultimately, though, the DOAS method represents a data analysis technique that retrieves this information about trace gases based off of the measured light spectra. And these spectra have to be measured in some way. And depending on how these measurements are made, you can oftentimes result in very different values of your final data product, especially when measuring scattered sunlight on the surface, which is typically known as multi-axis DOAS or max DOAS. Now, the basic operating principle of these types of measurements allows for making comparisons between measurements made at some viewing angle looking away from the instrument with a direct zenith measurement looking directly overhead of the measurement. On the other hand, comparisons can then also be made between exclusively zenith measurements, providing a more accurate description of the trace gases that are present directly overhead of your instrument. Now, both of these viewing geometries are surface-based measurements and ultimately are limited by the amount of spatial coverage that the individual instruments can actually provide. And so in order to provide a more global coverage, in order to see how these trace gases are impacting the entire planet, multiple DOAS instruments have been launched on board of satellites in recent years in order to provide a more global coverage of their measurements. However, as a trade-off to this coverage, these instruments have a fairly low spatial resolution, looking at swaths on the ground of individual detector pixels being between around 3 by 5 kilometers, which for most of the planet, this would be more than sufficient in order to identify any isolated sources or transport patterns that might be occurring. However, issues are run into, and particularly in urban environments and other industrial locations where there's a large number of potential sources that are present, which can further complicate these types of measurements such that the satellite-based measurements aren't going to necessarily be able to resolve specifically what is causing the high amounts of emissions that are being seen in these areas. And so in order to better quantify how these sources are impacting the satellite-based measurements, as well as to validate these measurements to make sure these satellites are providing high-quality data throughout their lifetimes, there have been numerous instrument networks that have been established all over the planet in order to perform these tasks. One such network, and has been the focus of a lot of my research, is known as the Pandonia Global Network, or PGN. Now, the Pandonia Global Networks operates these Pandora instruments, one of which can be seen in the image right here to the right, and are primarily interested in measuring two trace gases in particular, nitrogen dioxide, or NO2, and formaldehyde. These trace gases have very strong and unique absorption spectra within the wavelengths that are measured by these Pandora spectrometers, and also have very unique behaviors that can be used to estimate the behaviors of other less easy to measure trace gases. For instance, NO2 has a very short lifetime and typically remains distributed in the direct vicinity of its sources, which makes measurements of NO2 ideal for identification of what exactly sources are present in an area. On the other hand, formaldehyde remains more well mixed in the atmosphere and is able to travel over much longer distances than NO2. And so by identifying large amounts of formaldehyde in particularly source-free areas, it becomes an excellent tracker of pollution transport. Now, typically, Pandora instruments are operated at fixed locations where they only ever are moved for maintenance or repairs as necessary. However, Virginia Tech operates 3 Pandora instruments that don't necessarily follow these rules and are typically moved around from particularly interesting location to location and participating in field campaigns and other such locations and areas that have been identified as places of particular interest where more intensive measurements need to be made that whatever instruments are located in that area may not be able to provide. And so one particular area of interest and has been largely the topic of my research is Houston, Texas. Now, Houston is a very interesting location because not only is this the largest city in Texas, Houston is host of quite a few very interesting sources of both formaldehyde and NO2, which when combined with its proximity to both the Gulf of Mexico and Galveston Bay, lead to very interesting configurations within these trace gas emissions and transport within the area. Many of these major sources include large petrochemical refineries in Baytown, which are responsible for refining oil not just in Houston, but throughout most of the oil that is extracted in the Great Plains region. And stretching between Baytown and Pasadena, both along the Houston Ship Channel and the Buffalo Bayou, is numerous very large industrial sites making use of many of these secondary products of this refining process. In addition, directly south of Baytown, there's a large port of Houston, which is responsible for exporting this oil and other products, both across the nation and across the world, leading to large amounts of large container ships being present in this area. In addition, further south, there is Texas City, which in a similar vein to Baytown has numerous large refineries that are themselves responsible for refining oil extracted in the Gulf of Mexico. In order to better understand how these sources are all interacting with the city of Houston as a whole, 2 recent field campaigns have been held during 2021 and 2022, known as Tracer AQ1 and 2. These 2 field campaigns were hosted by the University of Houston and included not just Virginia Tech researchers, but researchers from other universities and government agencies, each bringing in their own unique methods of measurements of these trace gases in the atmosphere to come to a more complete understanding of how these trace gases are interacting within the city. And so in order to provide an adequate measure of just how these trace gases are interacting, to bring together data collected from the Virginia Tech's Pandora instruments, as well as collaborations from other universities' data sets, in order to come to really 2 sets of descriptions about how these trace gases are distributed, both vertically and horizontally. So this includes both 2 Pandora instruments, which have been taking max DOS measurements in 2 fixed locations, one looking behind the lab, behind a mobile platform, or just a van or a vehicle, really, looking at emissions that are along the path of the road that was traveled previously by this vehicle, with another instrument looking perpendicular to the vehicle to look at off-road emissions such as from industries. Both instruments were also taking zenith DOS measurements in order to represent the trace gases that are actually directly above the instrument in order to provide an adequate comparison between looking away from the vehicle itself and what is directly at the vehicle. To supplant these zenith DOS measurements, there are also in situ instruments collecting information about the concentrations directly at the surface of the vehicle, and further estimations of the boundary layer height, which represents the lowest atmospheric layer where short-lived trace gases like NO2 and formaldehyde will typically be interacting with the entire day, from backscatter measurements by LiDAR. One issue, however, with these types of measurements was that during both field campaigns, there were limitations of the instrument configurations, with the first Tracer AQ being limited to only 1 Pandora instrument, which was operating fixed into a zenith configuration. However, this presented a pretty good opportunity to separate these distributions of trace gases into 2 separate quantities, looking specifically at how these interactions are occurring vertically versus how they're occurring horizontally. And so by comparing in focusing on the relationship between the surface in situ measurements and the zenith columns measured by the Pandoras, we could take these lessons learned on the behaviors of these trace gases vertically into comparisons and to further comparisons during the second field campaign, now looking both at these vertical distributions and how the behavior of these trace gases are looking horizontally. And so in order to quantify how this relationship occurs between these Pandora zenith columns and these in situ surface concentrations, you can look at the column to surface ratio, which represents an estimated height of a well-mixed trace gas column, which with a concentration throughout this column matching that which was measured at the surface. While this isn't necessarily an accurate estimation of the distribution of this trace gas, we can make comparisons between this column to surface ratio and the boundary layer height to better understand how these trace gases are distributed within the boundary layer itself. Like for instance, if we have the majority of your trace gas situated closer to the surface, we would see column to surface ratios much less than the boundary layer height. And then as the distribution increases in altitude until we start seeing the majority of this trace gas is well above the surface and unmeasurable by these in situ surface instruments, we'd see the column to surface ratio sitting ideally or most likely even higher than the expected boundary layer height, which should be theoretically serving as a limit for how high these trace gases should actually be. And so by determining what the typical behavior of these trace gases is, we can further identify particular locations of interest by looking at where these trace gases are behaving atypically. This can be seen especially well on September 24th during tracer AQ1 with the measurements of nitrogen dioxide. So typically, due to NO2's short lifetime, you expect to see the trace gas distributed mostly close to the surface with values typical to what is being seen in the early mornings and the later afternoons on this day. However, during this time, there are two instances where we see the column to surface ratio rising well above the direct surface layer and being more well mixed into the upper parts of the boundary layer, sitting between about 200 to 400 kilometers over extended periods of time. Now, these time periods are occurring to mobile measurements that Pandora was making as it was traveling in residential areas in the direct vicinity of this industry that was situated along the Buffalo Bayou. This behavior shows that when these measurements are made closer to the surface, we may be seeing decreased values at the surface, but with higher columns, or at least more consistent columns throughout the area, likely due to the proximity to these measurements causing their emissions, which are typically elevated due to the emissions from like smokestacks and other such upper extend, I guess. Yeah, so sorry. That we can see these from, say, we can see this elevated amounts when in a particularly close proximity to these smokestacks, which are doing most of the emissions from these industries in the first place. Formaldehyde, on the other hand, is typically more well mixed, and we see that most of its column to surface ratios remain much higher and much closer to the top of the boundary layer height. However, we also notice during this analysis, especially on September 21st, multiple instances where there's a very interesting pattern in the column to surface ratios behavior, where we see a sudden peak followed by a very sharp drop off of this ratio. These are likely due to, once again, elevated emission sources from smokestacks and other elevated locations, I guess, performing the actual emissions of these trace gases. And then as this formaldehyde travels further away from these the original sources themselves, they begin to mix much more closely into the surface area, becoming much more impactful to those living on the ground. And so now that we have a decent understanding of how the vertical distributions of these two trace gases behave, we can now incorporate this with a description of how horizontally distributed these trace gases are. This is measured through the horizontal heterogeneity index, which represents the difference between various max Dulles viewing angles with the vertical column density measurements made from the zenith measurements directly overhead. This index is typically will be able to use to identify particular areas of interest where these measurements begin looking even more different than they normally would be, with particularly rural areas, which can be seen on September 13th during this large loop that was made around the southern section of Houston. We see during the southernmost part of this trip, which is a much more rural and remote area, so much more separated from the actual city of Houston proper, we see that these values are quite low. While looking back in the center of the city and along the coast of Galveston Bay and the industrial sites along Buffalo Bayou show much higher values of heterogeneity index. And so by incorporating this index along with the column to surface ratio and analysis on the differences between the measuring directions themselves, we can ultimately pinpoint where these sources are located that are affecting these differences in measurements and determine transport patterns within these areas. So one excellent example of this effect can be seen on September 13th during tracer AQ2. Except now, rather than looking at the formaldehyde during this large loop made, we can focus instead on the NO2 values that were measured in the very first part of this loop that was made as the Pandora instruments traveled southbound along the coast of Galveston Bay. Now, as the instruments were moving south, this led to two very different behaviors depending on the measurements, the max Dulles measurements that were being made. With the perpendicularly measuring instrument, which in this case was measuring to the west, seeing consistent average values throughout this leg of the journey, while instead the instrument measuring behind the lab, looking to the north, sees particularly high values, especially in the vicinity of the port of Houston, which has been starred. Now this means that there's one of likely two major sources which could be contributing to these values. Either A, surface emissions, largely due to vehicular emissions, or the Port of Houston itself, which would constitute more of an industrial emission, which should be behaving much more similarly to the emissions that we had noticed during tracer AQ1. Now, looking at the surface concentrations, we see particularly high values in this area as well, which would imply that most of these differences are due to largely vehicular emissions. But looking down at the column to surface ratio at the bottom, we see that this column to surface ratios of NO2 are much higher in this area than we would anticipate, being once again between 200 to 400 meters, similarly to what was seen during tracer AQ1. This leads to a reasonable assumption then that no, vehicles were not actually responsible for these emissions patterns, and that likely something further to the east, which would correspond to the port, is transporting its trace gases a little bit further to the east, or excuse me, to the west, than simply remaining directly overhead of the port itself. This is further evidenced by the reported winds on this day being easterly, which would mean that the trace gases, or the NO2 that was emitted at the port itself, was being transported over a very short distance and ultimately remained constrained to along the coastline and in between the port and the highway itself. Now, on the other hand, we can take a look at formaldehyde and see how patterns in its measurements can be used to take a look at transport patterns. Now, once again, we return to this area to the south of Houston, which is largely rural, except now, rather than seeing very low values in this area, we see particularly high values of formaldehyde vertical column densities on the instrument measuring directly to the north as the instrument travels westbound area. While looking to the east, behind the lab, we see similarly to the NO2 previously, average values that do not necessarily show anything in particular in this area. This would lead to a reasonable conclusion that there is likely some singular source within this area that's transporting this formaldehyde into this otherwise source-free area, which would likely correspond to a power plant which has been started on these plots. However, by incorporating the zenith tropospheric vertical column densities and taking a look at the heterogeneity index, we see not one, but two particularly high hotspots of formaldehyde heterogeneity, seeing one directly south of the city center of Houston and one just a little bit southwest of the power plant itself. These are likely corresponding to two separate sources instead of one, with the westernmost hotspot most likely being directly affected by the power plant itself, with the easternmost hotspot corresponding to emissions transport from the urban core of Houston itself, which has traveled over a much longer distance. And as such, we see in this area that the formaldehyde column to surface ratios are a lot more well mixed in this area, especially when compared to the very high values that are seen in the hotspot directly being affected by the power plant itself. And so from this comparison, we then can see that this area is not just being under the effect of really any one major source, but through the interaction of these two sources, we're seeing a lot higher values of formaldehyde than what any individual one could provide. And so just to wrap up pretty quickly, we have two major methods of analysis of these trace gases and their distributions within the atmosphere that we can use to come to a better understanding of how they're interacting than simply paying attention to one or two particular measurements individually. We can make use of the column to surface ratio to describe how the vertical distributions of trace gases are behaving, while also incorporating this with the horizontal heterogeneity analysis to identify prominent sources and to describe what the contribution of transport is being impacted over a specific measurement area. So thank everybody again for listening. And are there any questions?
That was good. That was very well done. Very cool.
I have a question.
Sure.
Can you go to the slide of the horizontal heterogeneity index?
Sure.
Where you introduce that? Yeah, so here in that equation,
Yes.
what is the index I? Is it latitude or?
Oh, so yeah, so for each, it's a summation of each individual max OS direction. So in this case, what you're seeing here is two measuring directions. So you have two VCDs of I, which are being compared to the zenith measurement made directly overhead. And so this leads to two summation of just two measurements. So then you have the summation of those two differences divided by two.
What I meant is, what is the I? So I, the index over which you are summing, are those different locations?
Right. So each instrument's taking very close to identical measurements at the same time. And so you can essentially be able to take each individual measurement and compare them against each other.
I see.
And so you've got two different measuring directions, one looking behind the lab, one looking kind of to the right, perpendicular to the vehicle, and one looking directly overhead. So you take the comparison of this one, and then the comparison of this one, and then average that together.
Got it. Thank you.
What role does diffusion play in any of this?
So, you mean just like natural diffusion or like?
Well, when I've seen stuff come out of a smokestack,
Right.
you kind of see it disappear after a little while. You don't see a column that permanently goes. So that means diffusion is spreading out those molecules.
Right. Yes.
Right?
So
It's not
typically,
staying
yes.
away.
So when you see those plumes like that are diffusing in the atmosphere, this is largely due to air currents and short range transport, not just moving them along in a particular direction, but also blowing into them and,
Well, when you talk about winds, that's advection, right?
Mhm.
Winds will take a column of molecules and just move it,
right,
but it won't change the relative concentration. Diffusion is spreading them out, and that's
Right.
what's gonna change the concentration.
okay,
And you mentioned near sources, you see the NO2 up high, but not down low.
Mhm.
Which would tell me diffusion is not operating on that.
right,
But say the formaldehyde,
right.
it's more well mixed. So I know it lasts longer.
Okay, yes, so it's largely based off of the lifetimes of these trace gases in the atmosphere. So NO2 has a lifetime of typically about an hour or so in particularly urban environments before it gets converted into some other chemical. And so this typically doesn't give it enough time to transport or diffuse over any significant parts of the areas. Formaldehyde typically lasts for multiple hours and even sometimes during the entire day. And so this will allow it to travel over much larger distances and remain a little bit better confined.
Yeah, that's
Yeah.
wild. That says the diffusion time is only hours,
Mhm.
right? If you see it well mixed.
Yeah.
That's wild. So it's significant, diffusion is significant for formaldehyde and negligible for NO2, even though the difference is only a few hours.
Right, yeah.
Wow, that's wild.
Any other questions? Online? Yeah, a couple people here. I thought there was some.
It's a minor request. Next time you present, can you add slide numbers on there?
Yes, I certainly can.
I thought it was really good.
Thank you.
I guess the only thing I was gonna think of with this route, it looks like you've tried to cover a lot of the different places. Can you highlight where, I think you mentioned Texas City?
So Texas City would be, let's see, yeah, so, and this area right over here,
Yeah.
particularly much further south, and then this trip, the instruments we're making.
Okay.
Mhm.
Yeah, that's
So,
one thing.
yeah, you can kind of see, right here would be the Port of Houston.
Yeah.
And then the waterways and this area to the north of where it was traveled here is the Buffalo Bayou and the Houston Ship Channel, where a lot of those industries are sitting around.
Okay.
At one point, you showed a plot that I think was mixing ratio as a function of altitude and showed it
Mhm.
drop
Yep.
at the top of the boundary layer. Am I interpreting that right?
Yeah, so generally, like NO2 and formaldehyde are also short enough lived that it takes them a lot longer to transport above this boundary layer than it does for them to get from the surface to the top of the boundary layer.
Right.
so they
What's the
typically-
physics of that? What's happening at the boundary layer that means transport is slowed down across that?
This is a bit of outside, I guess, of my scope of my research, to be honest, but typically I've found that to be just due to, I think I'm pretty sure it's largely dependent upon aerosols and how they're interacting in the atmosphere.
But it would seem
I
like
could-
if it's gonna be that, it's got
Mhm.
something to do with the temperature gradient, right? If it's
Right.
gotta be something.
I could certainly look it up and be ready for it next time I need to give this presentation.
Okay, well, one thing, as somebody who works up high
Mhm.
and now looking
Yeah.
at this, I'm gonna read your dissertation. Right? So like to do this column density
Mhm.
versus volume density. You have to know something about the height,
Yeah,
right? So if it's
Mhm.
well mixed, it's infinity,
right.
right? If it's not. Right, you got some boundary layer height.
That's right.
Assuming it's uniformly mixed
Mhm.
all the way up to there. I would need to know all about diffusion timescales and what's happening at that boundary layer
Mhm.
to slow down diffusion. Because
Okay.
you're assuming this sort of rigid
Mhm.
top.
Right.
But I admit, I don't know the physics of the boundary layer to know what that is.
All right, yeah.
It sounds like the way you're using it is a temperature inversion. But I don't know. There's definitely not always a temperature inversion everywhere you go,
Mhm.
right?
Yeah.
So,
I could certainly go and see what mechanics are really driving this boundary layer height and
okay,
provide a much better explanation of it
that
later.
might be so obvious to people who work in this altitude region that they don't normally write in the paper,
Right.
but I wouldn't get it.
Oh, yeah,
if you
100%.
Explained all that. This is fun. It's
Yeah.
interesting. It's very different.
Yeah, it makes me think of, we were with ballooning, right? It's a similar thing, right? Where,
Mhm.
yeah, we usually, we actually have some people who are looking at, not formaldehyde, but some other things. But yeah, we're gonna quickly get beyond that, 500 meter kilometer altitude really quickly, so that'll be interesting. So this, it's sort of like a, I guess, a preview for what I might see,
Yeah,
some of
okay.
our results and what's gonna happen. Kind of above that.
I think for Kevin, working with balloons and radars fixed to the ground and me working with satellites, we would love to be able to put our instrument on a van and drive it around.
Yeah.
Yeah, yeah. Yep. No other questions, and we'll call it a wrap there, and, but yeah, we'll have, I think before I was recording or whatnot, we'll have maybe before, a lot of people join or more people join, we'll have another seminar next week, since the following week will be Thanksgiving, so we're gonna push one up, and it'll be Shreya, presenting it. Not to put you on the spot, but.
I expect good cookies like you.
I'll have the cookies, don't worry. Right, thank you for joining us.